In this lecture, we're going to take a look at one of the most present and lucrative mathematical models that we encounter in our day-to-day lives, and that's the Google PageRank algorithm. I remember the first time I ever used Google, I was probably in high school, and what had happened was I opened up the newspaper, I think it was the Raleigh News and Observer, and I read an article that said, hey, there's this new website called Google, and just based on my experience, whoever wrote the article, it's a lot better than, say, the Yahoo search engine. So I remember trying it out and being pretty impressed with the specificity of what I was able to search for in Google and how well the results reflected what I was looking for. That was like 20 years ago. So given the keywords that you type into Google, how does Google decide what the #1 result returned to you is? Now, there are other considerations nowadays. I think geographic considerations are taken into account. So if you search for a chain restaurant, you might get something that's local to you versus the same restaurant on the other side of the country. And then you also get ads and things like that based on, say, websites paying for search engine optimization. But in general, let's just say you do a basic Google search and it returns 10 websites to you. How did it identify those 10? So if you search for sports, why would it return to you ESPN.com above, say, some local sports team in a different state? Okay, the main idea here is that web pages have some level of importance. So the PageRank algorithm that we're going to look at today takes websites and associates to them a number that reflects how important they are to society. The higher the number, the higher you appear in a search result. How do they determine importance? Well, the idea is importance gets shared when pages link from one to another. So let me describe this notion of sharing importance. If I take, say, my web page, which I think is now defunct from my graduate student days, and I link it to ESPN.com, then anyone who visits my website is more likely to then go on to ESPN.com. They might see the link and click on it. So I'm giving some importance to ESPN.com, but they're not going to get a lot from that because I have such a small website with very few visitors. Now, here's what you would want to happen if you want people to visit your website. You would want a big website like ESPN.com to link to you. And that's because the millions of people who go to that website are more likely than to visit mine. So if website A links to website B, importance flows from A to B. So if you want more importance associated to your website, you want other websites to link to you. You creating links doesn't do much, but other people linking to your website would allow their importance to flow to you, giving you more importance, ranking you higher. Okay, I think we've got the idea now, so let's go ahead and dig into the mathematics a little bit. So where does this notion of importance come from? How do we set it up? How do we calculate it? That's what we're going to look at. We're obviously not going to talk about the entire World Wide Web because it's huge, so let's pretend that this is the internet. There are 6 web pages, page 1, 2, 3, 4, 5, and 6. Ultimately, what we're going to set up is a transition matrix. We'll call it a hyperlink matrix that's going to tell us how links happen from one page to another. So what are the entries in this going to be? Well, just to write down a precise algorithm for how to set up this matrix, let L sub j be the number of links emanating from page PJ. So if I look at page 1, for example, I've got 2 links coming out of page 1. Sorry, the arrows are so tiny, but we have an arrow pointing from page 1 to page 3. That indicates that if you're on page 1, you'll see a link for page 3. And likewise, we have an arrow from P1 to P2. So visitors to page 1 will see a link to page 2. And those are all the links coming out of page 1. So L1 is 2. And if we look at page 2, visitors on page 2 will only see one link to page 4. So L sub 2 is 1. L sub 3 is going to be 1, 2, 3, 4. So page 3 links to page 1, page 2, page 4, and page 5. L sub 4 is 3. Page 4, it looks like, links to 1, 5, and 6. Page 5 only links to 4 and 6. So L sub 5 is 2. And then L sub 6 is 1. Before we actually proceed, let's take a step back and just look at this internet a little bit more. Just based on who's linking to who, which website do you think will gain the most importance? And just eyeballing this, I would say page 4, because look at all the arrows coming into page 4. Pages 2, 3, 5, and 6 all send visitors to page 4. Page 1 is the only one that isn't, but then page 1 is sending people to page 3, which is sending people to page 4, and to page 2, which is sending people to page 4. So it seems to me like page 4 is the most important website in this internet. Okay, so that might be our conjecture after we do the algorithm. We would like to see page 4 emerge as the most important. Okay, here's how we're going to fill in this hyperlink matrix. Columns are from, and rows are to. So what I mean by that is if you're in column 1, those are links from website 1 to the other websites. And then what's going to happen is if we're in column 1 and page 1 links to another site, in fact, let's just go ahead and do it. Page 1 is linking to page 2 and 3. Every website it doesn't link to, including itself, gets a 0. So 4, 5, and 6 all get zeros. And then pages 2 and 3 get 1 over 2, or half. So it's 1 divided by the total number of links coming out of page 1. So we'll do 1/2 and 1/2. Okay, from now on, I'm only going to fill in the positive entries, and you can assume the others are 0. So who is being linked to by page 2? Page 4. And that's the only link coming out of page 2, so it's 1 divided by 1 in the second column, 4th row. Page 3 links to 1, 2, 4, and 5. So each of those rows will pick up a 4th in column 3. So we have 1/4, 1/4, 1/4, 1/4. Actually, let me go ahead and fill in the zeros, and I'll copy this over so that it's a little bit easier to read in a second. I have these blank entries that might make it a little bit hard to see. Okay, page 4 links to 1, 5, and 6, so each of those rows will have a 3rd. Page 5 links to 4 and 6, so each of those will get a 1/2. And page 6 only links to page 4, so we get a 1 in the 4th row, and the rest are zeros. Okay, so there's our hyperlink matrix. A couple observations here. It's a transition matrix where the entries are like probabilities, but we assume that if you're on, say, the 3rd website, you have an equal chance to go to any of the links. So we associate to pages 1, 2, 4, and 5 probability 0.25. That means for the internet that we're looking at here, this is a stochastic matrix because all of the columns sum to 1, so that's good. Given that it's a stochastic matrix, we have some theory about what we can do with that, so let's talk about that. So our hyperlink matrix H is a stochastic matrix. All of the columns sum to 1. However, we do have some zeros here, so it's not what you would call a positive stochastic matrix where all of the entries are greater than 0. However, as I mentioned before, when we looked at transition matrices, even if the theorem that taking the matrix and raising it to a high power isn't guaranteed to be true if you have some zeros present in your matrix, it's still worth trying. It might work. So let me pull up MATLAB Online, and we'll enter in this matrix H. I'll show you a shortcut for how you can do that if you don't want to type all of these fractions. There's a way to to do it in MATLAB where you just type in zeros and ones and then you have MATLAB create the fractions for you. And then we'll take that matrix and we'll see what happens if we raise it to a really high power. So basically, we're going to hope that the columns all converge to the same vector. Okay, so here we are in MATLAB Online, and the first thing I'm going to do is create my hyperlink matrix. And what I'm going to do is just put in zeros and ones. So the first row is 0, 0, 1, 1, 0, 0. The second row is 1, 0, 1, 0, 0, 0. 1, 0, 0, 0, 0, 0. 1, 0, 1, 1. 0, 0, 1, 1, 0, 0, and then the last row is 0, 0, 0, 1, 1, 0. I just think that's a little bit easier than typing in all those fractions, and then also the columns all stack up nicely. So zeros and ones for now. And then to actually create the matrix that we want, you do H equals, we're going to redefine it in terms of itself, H array divided by sum of H. Sum of H is going to return you all the column sums. And when you do this operation, you get the actual matrix that you want. So if you check this against what we wrote down, it's half half in the first column, and then we have a 1 down here, and then we have page 3 linking to a lot of people, etc. Okay, so I think that's a little bit easier than trying to type in all those fractions. Again, you can always sum your hyperlink matrix when you're done, or sum your transition matrix, and all of the columns should add up to 1, assuming that you have a nice stochastic matrix. Okay, so there's our matrix H. If we take H and square it, then this is like a transition matrix where we're saying that the probability of going from page 2 to page 1 after 2 clicks is 1/3. There was no link from page 2 to page 1, but you could get there using transitivity. From page 2, your only link actually directed you to page 4. So after 1 click, you would have to be on page 4. But then from page 4, there were 3 links to 1, 3, and 6. So that's why there's a 1/3 chance that from page 2, after 2 clicks, you would arrive on page 1. Page 6 was another one that only linked to page 4. So after 1 click from page 6, you would go to page 4, and then there's a 1/3 chance you would end up back on page 6. If you start on page 1 after 2 clicks, there's a pretty big chance that you'll be on page 4. Similarly, if you started on page 5, with 50% probability, you'd be on page 4 after 2 clicks. Okay, so let's move on. What about 3 clicks? All right, the dust hasn't really settled yet, so let's try 30 clicks. Okay, here we can see what we'd like to observe. And that is that all of the columns are the same. If we do 300 clicks, I don't think we'll see a difference. Nope. So let me call this M, just for matrix. And let's have U be that first column of M. So all rows, first column. Okay, so there's our vector U. I claim U is that fixed vector that isn't affected by the actions of H. So if I take H and I apply it to U, actually let me do it so that we can compare U to H times U. This will be a matrix with 2 columns. The first is U, and the second is what happens when we do H times U. You can see that H fixes U. In other words, U is an eigenvector with associated eigenvalue 1. So let's go back to our slides now. Okay, so even though this wasn't a positive stochastic matrix, what we observed is that the long-term behavior still trends to the same fixed vector repeated in every column. That vector was 0.1404. 0.0877. Of course, I'm rounding to MATLAB's 4 decimal places. 0.0702. 0.3684. 0.1404. 0.1930. Let's call this first column our fixed vector U. And then, of course, we just repeat that 5 times. U is now the importance ranking of the pages. Because what it tells us is the long-term probability that on your next click, you're going to arrive on, say, page 4. So U is a vector of the importance rankings of each of these 6 web pages. So let's see what the result is. Well, the ranking level is highest for page 4, and that's exactly what we predicted just based on the diagram that we were looking at. So indeed, page 4 is the most important. What's next is page, let's see, looks like page 6. And then we have a tie between 1 and 5. Not sure how Google handles ties, actually. And then page 2, and then page 3. Okay, so let's ignore the fact that it's a little unclear here how you would list page 1 and page 5. Maybe you just alternate them or something like that. But anyway, so this is our importance result. Now let's say that based on your keywords, each of these 6 pages could be a response to a Google search that you do. What Google's going to do is put page 4 at the top because it thinks that you're most likely to click on page 4. That seems to be the most important website. And then page 6. Page 3 would be the bottom of the search results. That actually makes a lot of sense if you look back at page 3. It's only receiving one link from page 1. So that one link from 1 to 3, not from, say, the most important website to 3, but just from 1 to 3, really means that there's not a lot of traffic towards page 3. Page 3 is not very important. The example we just looked at worked out even though it wasn't a positive stochastic matrix. It was a stochastic matrix, but there were zeros in the entries. Now what we're going to do is talk through a couple other issues that could arise that might prevent taking the hyperlink matrix and raising it to a high power from being effective. We'll solve those problems, and what we'll end up with is a really robust algorithm for which our high power will always work. Okay, so the first issue is something that's really realistic. If you think about how the internet actually works, what if there's a web page out there that just doesn't have any links? So when we set up our matrix, the column corresponding to that website has only zeros in it because there are no links to other web pages. That's happening here in this toy internet. In particular, if you look at web page 2, P2, there are no outward links. Otherwise, I think this is the same as our previous picture, so let me copy over the matrix from before and we'll just adjust it. Okay, this was the matrix that we've already seen, except for now I'm going to take that link that used to exist from website 2 to website 4 and replace it with a 0. The problem here is that this is no longer a stochastic matrix because if I were to sum up all the columns, the second column sums to 0. Let's see what effect that has in MATLAB. Here's the hyperlink matrix that we had before. So I set it up with 1s and 0s, and then I divided H by its respective column sums. Now what I'm going to do is take this 1 in the second column and replace it with 0. When we do this, we have a little stumbling block in that the second column now consists of NaN. That stands for not a number. Let me just temporarily fix that. We're going to say H of all rows second column. This is a bit on the side because we're going to set up a new algorithm which will prevent us from seeing that. But let's do 0s, 6 rows, 1 column. Okay, so there's our matrix H that we want. Now if I do H to the 500, you can see the second column is never going to give us that fixed vector. That stays at 0. And then the other columns are all different. If I do 5,000, again, the columns are all different. So the algorithm doesn't work. So let's fix this issue on the way to having our final Google algorithm. So what we're going to do is create kind of like a preliminary matrix S. What I'm going to do is take that column of all zeros and replace each entry with 1 over 6. 6 because there are total 6 web pages in this internet. So it's like everybody gets equal benefit from page 2. So I haven't really changed anybody's importance too much, but now we have a stochastic matrix. Okay, let's go back to MATLAB Online. Here's where we left off. I could actually fix this second column on this line here, but let me just do what we did before. So what I'm going to do is put a 1 everywhere in the second column, and that way when we divide H by its column sums, we get 1/6. Okay, now this is a stochastic matrix. It's not positive, but let's see if we raise it to a high power and we get something we like. Looks like we do. You can compare the rankings here to the rankings that we already saw. It's almost the same internet, but not quite. But just eyeballing these numbers, you can see that page 4 remains the most important. Okay, so this is the first step we're going to take from our initial hyperlink matrix. We're going to do one more thing to it. And the motivation for the next step we take arises from this issue. So what if the web has disconnected or weakly connected groups of pages? Maybe every website links somewhere else, but then you get these kind of isolated rings linking to each other. Let's set up a hyperlink matrix for this internet. It's going to be different, so let me just do it from scratch. We're going to have a 6x6 matrix. We'll call it H to start with. And let's see, page 1 links to pages 2 and 3. So we're going to have 0, a half, 0, 0, 0. Page 2 only links to page 4. Actually, this is very similar to what we saw before, but whatever. So we'll do 0, 0, 0, 1, 0, 0 in the second column. Page 3 links to 1, 2, 4, and 5. 1, 2, 4, and 5. Page 4 only links now to pages 5 and 6. I think that's the big change compared to the internet before. Maybe there's something else different. But anyway, we get 0, 0, 0, 0, 1 half in the fourth column. And then page 5 links to pages 4 and 6. So that's going to be 0, 0, 0, 1 half, 0, 1 half. Page 6 links only to page 4. So 0, 0, 0, 1, 0, 0, and that's 6th column. What's going on here is that if you look at, say, the lower right 3x3 grid here, that represents how pages 4, 5, and 6 link. They don't link back to pages 1, 2, and 3. So it's like once you get in pages 4, 5, and 6, you can never leave. You could never go from page 4 to page 1. But we would like our internet to be a little bit more connected than that. So we don't want people to get trapped in wells from which they can't click out of. Okay, one remark I'm going to make is that we might as well call this matrix S because there was no change that we needed to do. So let's imagine we've already passed that first check. So we didn't have any columns of zeros, but if we did, we would go ahead and replace that column with a column consisting of 1/6 in each entry. What Google does is it takes a parameter alpha, multiplies this matrix S by alpha, and then adds to that this matrix consisting of the same number repeated in a 6x6 fashion for this internet. And that number is 1 minus alpha divided by n. Let's call this matrix G. This G is actually going to be the matrix that we would like to exponentiate to high powers. So let me set this up in MATLAB and then we'll see what happens when we raise this to a high power. Okay, so here's the hyperlink matrix that we had in the last example. Let me fix it now for the example that we're looking at. So let's go back to having 0, 0, 0, 1, 0, 0 in the second column. And then let's see what else is different. 4 no longer links to 1, but that was actually the only change. Okay, so here's what happens when I fix this matrix and then I run it to a high power. As you can see, everybody eventually gets trapped in that little sub-community of pages 4, 5, and 6, which means that pages 1, 2, and 3 would not get any importance, and that's not very fair. Okay, let me call this matrix S. just to make it match the notation that we have in our slides. We're not going to exponentiate S, we're going to exponentiate G. Alpha is some parameter. Let's set it to be 0.85. That's the current value between 0 and 1 it has to be. I actually don't know that that's the current value as of right now, but when I learned this algorithm, that's what alpha was. And then let's call it M. This is going to be 1's 6 by 6. So if you run that, you can see what M looks like. And then we'll take M and redefine it in terms of itself as 1 minus alpha divided by 6 times M. Okay, so there's M. You can see M isn't going to do a lot to the different importance levels because every column is getting affected the same way. But it's going to give us a matrix, G. G is going to be alpha times S plus M, which is a positive stochastic matrix. So in particular, if I do sum G, the columns still sum to 1. But if you look at G, because we add to the matrix S this little positive number, 0.025 in each entry, no entry is going to be 0. So we're not going to have some sort of network like 4, 5, and 6 that you can't escape from. We're essentially saying there's a tiny chance that from page 6 you would go back to page 1. That's not what the links tell us, but this is how we're going to adjust our matrix so that we can take it and exponentiate it to a high power. So if I do G to the 5,000, now the algorithm works. We see the same column gets repeated 6 times, so that's our fixed vector U from our theory on transition matrices. And the entries in that vector U give us a way of ranking the pages. So once again, with this internet that we've tweaked a couple of times, page 4 emerges as the most important website in this internet. After that, it looks like page 6, followed by page 5, then page 2, 3, and 1. Notice pages 1, 2, and 3 are not very important because we still have this internet that we were looking at where 4, 5, and 6 don't link to 1, 2, and 3. We couldn't fix that. We couldn't tell those web pages to create links. So that property that once someone gets into pages 4, 5, and 6, they won't go back to 1, 2, and 3. That's true about the internet that we were working with, but we fixed our algorithm so that they still get a little importance level, which is not 0. So that's why pages 4, 5, and 6 still have much higher levels of importance here. After making these changes, creating the matrix S so that we don't have any columns of all zeros, and then adding this term 1 minus alpha divided by the number of websites times a matrix of all ones to our scaled version of S, we end up with a positive stochastic matrix. We saw that emerge in MATLAB, but let's verify it by hand. The column sums of S are all 1, which means the column sums for alpha times S, taking S and scaling it by that parameter, are going to be alpha. What's a column sum for the matrix on the right? Well, we're going to have that expression 1 minus alpha divided by n added to itself n times. That leaves us with a total column sum of 1 minus alpha. So then when you add those matrices together, the first column gets added to the first column, the second column gets added to the second column. That means that the column sums for G are alpha plus 1 minus alpha. So our matrix is indeed stochastic. Moreover, we don't have any negative entries here. It's quite likely that in the matrix on the left we have zeros. But then we're going to add to that a little positive number. So the minimum entry is 1 minus alpha divided by n. So we conclude that G is indeed a positive stochastic matrix. By the Perron-Frobenius theorem, that means that G raised to a high power will go to a matrix with one column repeated over and over. And then the entries in that vector U allow us to rank the websites from most important to least important. At this this point, we're done with the basic Google PageRank algorithm. Of course, there's a little bit more that we could say about it and how it's actually put into practice, including how big is the internet? I mean, how big are these matrices and how much computational power do you need to do this algorithm? But the algorithm itself is pretty simple. It's a beautiful algorithm and one which, of course, we interact with on a daily basis. Thank you for your attention.